Thank you. Okay, hello everyone. My name is Ling Luo. I'm from BioMedical group at NCBI. Today I will present our new resource, BioRED, a comprehensive biomedical relation extraction data set. With the rapid of biomedical tags, automatic information extraction from literature is critical for downstream in research and real-world setting. Here I show a general information extraction pipelines. It contains 3 important steps. The first is name entity recognition, is to recognize the entity mentioned from the text and classify the relation type. The second is name entity linking. It will link the entity mentioned to a specific ontology identifiers. The third is relation extraction, is to extract the relation between entity pairs. Automated information extraction system can help us extract the unstructured knowledge from the free text. To promote the development and the evaluation of AI-powered information extraction systems, many significant works on development, dataset development has been proposed. Most exciting biomedical relation extraction datasets only focus on the entities and the relations of a single type at the sentence level. It limited the development of relation extraction system. Many relations from closed sentence and consistent of different entity pairs. Moreover, the exciting novel finding is more important than exciting background knowledge. But through our best knowledge, none of previous data sets annotation includes the novel annotations. So in this work, we propose a new data set, BioRED. It consists of 600 abstracts and contains rich entity and relations. We summarize the 3 unique features of the BioRED. The first is it contains 6 entity type and 8 relation between different entity pairs. The second is the relation can be from in a sentence or closed sentence. It is a document level relations. The third is the data set is enriched with the novelty annotations to distinguish between known facts and novel findings. Next, I will introduce our annotation scope. In the data sets, we annotate the 6 entity types, including gene, disease, chemical, species, variants, and cell-line. To reserve the terms variant and ambiguity, we normalize the entity mentioned to a specific ontology identifiers. For example, we link gene entity mentions to NCBI genes. Between of any entity pairs, we observed a popular relation pairs and other relations are implicitly and rarely discussed. In this work, we focus on annotate the 8 popular relations. Furthermore, to classify the relation type, we use 8 biological meaningful and undictionary relation type. For example, as shown in the figure B, for example, positive correlation and negative correlation. Furthermore, we propose a new task, novelty annotation. In this task, we assign a label to each relations. Here, novelty tag means the novel finding, and the non-tag means providing known background knowledge. As shown the example, the relation one is the background knowledge, so his neighbor is no. And the relation two is the main point and the novel finding in the abstract, so his neighbor is novel finding. Next, I will introduce our annotation process. To keep the consistent with previous annotation effect, we sample articles from several existing data sites. To speed up the annotations, we use previous annotation combined with automatic entity pre-annotations. Here we use our tool pubtator for entity pre-annotations. We first run the sample a small site to create our annotation guideline. We set the annotation process as a cycle. In each iteration, we first sample 22 PM IDs. Then the annotators will first annotate biomedical entities. After they finish the entity annotators, they compare the results and discuss the reference. Next, annotator will annotate the relations. After they finish, they will discuss the difference and they will compare the results and discuss the difference. In the process, three annotators work on entity and the relations, and the two annotators work on novelty. For the difference, after they discuss relations, one single annotator will review it and make a final decision. We use our annotation tool, TinTag, for annotators. TinTag is a web tool to management annotator projects efficiently. Here I show an example in the TinTags. As a result, we annotate 600 abstract. It contains about 20,000 entity mentions, according to about 4,000 unique entity identifiers and 6,500 relations. We split the data sets into training, development, and test site. The table shows the number of relation and the entity in the size. The average document contains about 12 sentences with an average of 34 entity mentions and about 12 relations per document. The figure shows the distribution of entity pairs and the relation type. 52% are associations and 27% are positive correlation. 17% are negative correlation. Remaining are others relation type. We evaluate the three state-of-the-art models on the named entity recognition tags, including BioSTM with CRF, BioBERT with CRF, and PubMedBERT with CRF model. We use F1 score metric as a metric. There are two versions. The first is string metrics. It requires entity type and boundary should exactly match. And we also use relaxed metrics. It requires the same entity type, but the entity boundary only require overlap. The table shows the performance of named entity recognition models on BioRED test site. We can see that the PubMedBERT with CRF model achieved the highest performance overall. And in string metrics, old models achieve over 80% F1 scores, and in relaxed matrix, our model achieved over 19% in score in F1. It suggests the state-of-the-art model achieve a promising results on the named entity recognition task. We choose the BERT GT and PubMed BERT to evaluate the relation interaction tags. We use the standard F1 score as a matrix. We evaluate the systems using 3 different schemas. The first is to examine the pair of entities within a relation. The second is classify the specific relation type for the exact pairs. The third is novelty to further enable the novelty for the relations. Older model tested on the gold standard entities. The results show that relation injection is very challenging. There is much room for improvements, especially for exacting novel finding. The best models only achieve 47% in F1 scores. Moreover, we also observe lower performance in variant and chemical relation type. The main results we think is the variance and the chemical relation type in dataset is not enough. These slides we explore the benefit of multiple entity and relation. Compare with training a single model with all entity and relations. We also trained multiple individual models, each with a single entity and a relation. From the figure, we can see that training a single model with all entity or relations generally achieve a better performance than trained multiple single models. Therefore, training named entity recognition or relation interaction model with more relevant entities or relations not only can reduce the resource usage, but also can achieve better performance. More recently, we are exploring how to use BioRED to improve the relation extraction systems. We got some results. First, we found we can use other corpora to improve the evaluation performance of BioRED. Here, we conduct experiments use 3 widely used data sets. From the figure, we can see that when we merge the BioRED and other data sets, can improve the performance of BioRED. Moreover, we also like to know if BioRED can improve the evaluation performance of the other data set. To each data set, we trained 2 models. One is we use only original training site to train the model. The other model at BioRED denotes we use original training site merged BioRED corpus to train the model. From the figures, we can see that aiding BioRED can improve the evaluation performance of the other data sets. In summary, we developed a high-quality relation extraction corpus with one of Ken novelty annotations. His annotations covers 4 bio-NLP tasks. We hope BioRED as serves a benchmark for developing relation extraction methods. Although BioRED is a novel and high quality data size, but there are a few limitations. The first is the data set only includes 600 abstract due to human annotator is very high cost. It takes over 2,000 annotator hours. But our experiments show that except for few relation type, the size of data size can build relation extraction models. The second is not the data size is annotate on PubMed abstract, not full text. Annotate on full text is very challenging. We will address it in our future work. More recently, our manuscript is upside by briefing in bioinformatics. His print version is on archive. You can find more detail on our manuscript, and the BioRED dataset and annotation guidelines are freely available at our group FTP. You can also scan this QR code to visit it. Finally, thank our group research members and our partners. The work was supported by the ARP of NIH. One more information. My PI, Dr. Ling Luo, will give a keynote talk at Canada tomorrow, 10 and 30. If you want to know more detail of our group work, welcome. Okay, thank you for your attention.
Thank you very much for a great presentation. Do we have any questions from the audience or online?
In the chat for questions.
Okay, let's start with from the chat then. Can you see them here?
Did you pass the data for fine-tuning sentence by sentence
We are
or
opening
the whole
Q&A.
abstract at once? The first question. Yeah.
Do you pass the data for fine-tuning sentence by sentence or the whole abstract at once? If the whole abstract, do you must have occurrence of the source and target entity interesting in the text? Okay, in this question is for the I think it's for the relation extraction info models. In the experiments, we use the whole abstract as the input. We didn't master entities in the text. We keep the entity or original entities. Yeah, this is the question 1. And question 2. What do you think could help to improve the performance of the relation extraction text, more data, or for example? Okay. Yes. If we have more data, I think we can train a better models. But create annotated more data is very high cost. Especially annotate multiple relations and entities. So I think we can use some ontology or database to improve the relation extraction. For example, CTD database. The database includes a lot of manually annotate relations. So I think we can use some exciting data set to improve the relation extraction.
I think we can take one last question if there was one last. Otherwise, we move on.
How to use our own abstract using BioRED? How to use different data corpus? Okay, because this experiment is done by my colleagues, so I don't know the details of how they can combine the different corpus. But I know we can try different combined methods. The first, we can simple merge the data set, and we also can use transport learning to use the different data set. Okay, I think,
Yeah.
yeah, thank you.
Thank you very much again.